Okay, everyone. I guess we can start now. Welcome again. This is session 6, and as you can see from the schedule, we're focusing this week more on basically the technologies. So the technologies that we're leveraging to potentially solve the problem. So today we're doing space, and then on Friday it's more on UA technology. And the speaker today is actually Eric. So he wears a different hat. This time around, representing SpaceBase and International Space Consultants. He'll talk probably more about his background, but he's actually worked for 3 decades working on either space-related projects, NASA, and also space startup companies, mostly in the US and also in Europe. So I think I'm just gonna turn it over to Eric, and then he can start.
All right. Yeah, hello everyone. I'm Eric Dahlstrom, part of the SpaceBase here in New Zealand. In the chat area, I posted a link to the folder where you can find the PowerPoint file for this presentation. A lot of the value in this presentation, I think, are in the links, and the links should be active within the PowerPoint file. And so, yeah, please go ahead and download that when you have a chance, and I'll show you some of the more interesting links in this presentation. Let me start by sharing my slide with the presentation. Let's see. Okay, yeah, this is generally about space technologies, and some of this is general background information that we have such a wide range of backgrounds in the participants in this, on the teams, that some of this may be pretty basic for people, but I just wanted to establish a common understanding for basic things like orbits and sunless satellites. And then also I want to give you some illustrations of investigating some details about some of the spacecraft and wavelength bands. So let's see. Here we are. So this is my general outline. I wanted to talk about the satellite basics of the launch and inclinations and orbits, give some examples of different Earth observing spacecraft and how the technology has changed on some of them, and talking about some of the sensor systems, and investigating some of the wavelength bands. It is like a puzzle trying to figure out for each individual spacecraft the details on what wavelengths they're measuring in the different bands, and talking a little bit about some of the future systems. So just in general about the history and trends in the industry, this is a history of all space launches back from the early days, and you can see back when it was dominated by government launches from the US and the Soviet Union, and partly was because the Soviet Union was launching regularly very high frequency of spy satellites. They were dominating the launches. But in recent years, you can see down here that we've shifted towards commercial launches, and they've had emergence of companies like SpaceX and now Rocket Lab doing commercial launches. Then another trend over here is that just in the last few years, the smaller satellites have been dominating the number of launches, especially ones such as the Planet Dove constellation or Spire Global. And so these are, I'll show you later, are really tiny satellites that are launched dozens at a time. Even a small Rocket Lab launch vehicle can launch 20 or so at once. And so suddenly we've had an explosion of the number of satellites, even if they're very small. So just a reminder about some of the scale of the launch vehicles. We have Rocket Lab's Electron over here on the left, and SpaceX Falcon 9 on the right. And you can see this, the SpaceX Falcon 9 is competing with the ULA Atlas V, and 19 tons or 22 tons to orbit, whereas Rocket Lab is in a different class. It's launching about 225 kilograms at only $5 million. Per mass, it's actually it's more expensive. I mean, if you had a huge number of satellites going at the same time, it'd be worth it to buy a Falcon 9. But if you're just trying to add one or two small satellites onto a launch vehicle, the Falcon 9 is an expensive proposition, and it basically, and typically if you're a secondary flight, you're not deciding where you're going exactly, and you have to work to make your satellite go to the right place, right orbit later on, whereas the Electron will deliver you where you want to go. Down here on the left, there's a little diagram of the rotating Earth, and if you're going to launch to the low inclination orbits near the equator of the Earth, you get a boost by launching from a location near the equator on Earth and launching to the east. And so that's why a number of launch sites like Florida or French Guiana, or some of the launch sites for Japan or India are located near the equator and open up to going east. And you can see the directions you can launch in those directions. If you're going to launch into the polar orbit, north-south, it doesn't matter if you're launching north or south, but you want to be launching either towards, here's Vandenberg in California launching to the south, here's Plesetsk in Russia launching to the north, and so all these different launch sites have different constraints, especially if you're in Florida, or in the U.S. On the coast, you want to be launching with parts dropping in over water. China has controversy because they drop their components of their rockets over populated areas within the country, and so even India has now decided that if they're going to polar orbit, they actually take a bend and go around Sri Lanka to avoid the populated areas. And besides populated areas, there's also all the air and ship traffic, which on a large launch from Florida, you can actually shut down air traffic around Florida for hours. And so that makes a huge disruption. And you can see way down here, New Zealand, with a pretty isolated or empty area around air and ship traffic to the south and east, and that makes a great convenient spot for access to launches at all times of the year. And so that's why you end up with launches from the Mahia Peninsula either due east for equatorial launches, or if you're going to polar orbits, pretty much south, straight south. And so here's the Rocket Lab launching from New Zealand here. Just in general about the orbits you're going to, I wanted to illustrate this and see if I can, let me see if I can switch over to this. This link will get you to this live site. Let me try this. Okay, here we are. See if this works. Yeah. Okay, this is a guy who's been tracking satellites on a semi-official basis for 30 years or more. He's based in Hawaii. And this is just a nice illustration of where these spacecraft are. I wanted to illustrate the difference between a geosynchronous Earth orbit out here, which is way out about 6 times the radius of the Earth out here, and it's in an orbit that matches the speed of the rotation of the Earth, and so something out here appears to hang in the same space in the sky. Let me see if I can animate this a bit. And so that's pretty slow. Let me speed it up. Okay, so now as the Earth rotates, GEO is going to stay in the same place in the sky. But these other spacecraft are down in low Earth orbit, and almost all these satellites that are Earth observing are in sun synchronous orbits. And here you see that at a particular time of day, they will pass over New Zealand, and oftentimes they're labeled by when they pass over when they cross the equator. A lot of them cross the equator at 10:30 in the morning, and then there's also the radar satellites, which are that synchronous with the sun, but stay close to the Earth sun or the light and dark transition, the twilight zone here, the shadow zone, and so because it's northern hemisphere summer right now, the orbit doesn't quite match the angle of the sun shadow region, but so you have designs of certain satellites, constellations like planet Pleiades A and B, that are following each other in order to give a repeat observation and with a short period of time. But it's but also because of these satellites are in these fixed orbits, and the Earth is rotating underneath them, there's can be a long time between a revisit period. So if you have to wait, quite a bit of time before you are rotate around under sunlight under the same satellite orbit, and so it's that revisit time is a real limitation for a lot of these big remote sensing satellites, and that is. And we'll talk about in just a moment the alternative that Planet has come up with. Let me switch back to my PowerPoint here. So in general, there's geosynchronous Earth orbit, where mainly there's a lot of communication satellites, and but some remote sensing satellites, a lot of meteorological satellites. It's very difficult to get very much high resolution from that distance. And then you have a lot of low Earth orbit satellites, and quite a few of them are in this polar sun synchronous orbit. And here is another illustration around New Zealand of some of the NASA and European Space Agency and Airbus proprietary satellites on the left, and then the more than 200 small CubeSats that Planet operates, that are trying to do a full scan of the Earth every day, with around between 3 to 5 meter resolution. Let's see if I can get this. So you can see that it's quite a challenge to just keep track of all these individual Planet satellites that Planet is monitoring from their, and where they're monitoring from their headquarters in San Francisco. And let's see. So I mentioned the sun synchronous orbit. It turns out that for the equatorial bulge of the Earth and other factors, that orbits that are in high inclination or going north-south, they are affected by the equatorial bulge of the Earth and process around and move around. And it turns out that if you pick exact combinations of the inclination and the altitude, you can get it to the orbit to precess just exactly this to counteract the Earth's rotation around the sun, like 1 degree a year, right? 1 degree a day, roughly. And so, but you have to do it very precisely. So if you choose an orbit altitude for your Earth observing spacecraft, something like 500 kilometers, you go up and you get this very precise, 97.4 something degrees of inclination. If you match that inclination, then you can be perfectly sun synchronous, so that as the Earth rotates around the sun during the year, the orbit will advance just at the same angle, and always keeping at the same angle with respect to the sun. And so that just makes it more convenient for looking at the ground in the same angle from the sun. So it's just it's an artificial kind of choice that was made to make the remote sensing analysis a little easier. Let's see. So in another trend from the last 20 years is that it used to be that the spacecraft hardware and bus structure, the power system, data system, everything like that was really expensive, and so the design choice was to put like 5 major instruments on one giant spacecraft, and that's an example is the Terra Earth observing system morning crossing spacecraft, and so that was this thing is the size of a bus, and it's 5 tons, and it cost $1.3 billion to build. Launched 20 years ago, and still operating. And but it's one of these things where it's a massive set of these major instruments, and the several of the instruments are beginning to fail in different ways. But this kind of attitude of putting everything together in a giant spacecraft, that trend is people have moved away from that, especially because there was this one project I worked on called NPOS that was a combination of weather satellites and research satellites and military weather prediction, and one instrument was late, and the entire $8 billion program got canceled because of it. And so it was people began to realize that it makes a lot more sense to just put these satellite instruments on individual satellite buses, because the satellites themselves were decreasing in cost. So here, for example, is the fleet of the Airbus proprietary operated satellites, and so everything from the TerraSAR, the synthetic aperture radar, and the Pleiades and Spot, and the PAS is another SAR spacecraft that was just launched, and then they have plans for future versions of the Pleiades spacecraft. But each spacecraft carries one instrument basically, and you can see that the trends of the sizes of from the very big high resolution world view satellite. In fact, Earth observing system would be like off the scale of this picture. It's really big, and then here's the Pleiades, big, basically a 85 centimeter telescope pointed at the Earth, and then all the way down to the tiny little Planet Labs CubeSats. And here's illustrations of the CubeSats. There are 3 called 3Us, which means they're 30 centimeters by 10 centimeters by 10 centimeters, and but they can still get imagery at the 3 to 5 meter scale, and you can see that they're being mass produced by Planet. Part of this different change in engineering concept is going from a waterfall to agile kind of implementation, where they're designing the next iteration even while they're building the previous iteration. So they're up to like, I don't know, 20 iterations so far. Just as an example of investigating some of the details on spacecraft like Sentinel-2, Sentinel-2 is a very good quality and freely accessible satellite. The data is freely accessible as from the built by the European Space Agency and operated for the European Union under the Copernicus program. And this website gives you information about their user guides and technical guides, and you can see that the different Sentinels have different are focused on different things. Sentinel-2 happens to be this multispectral imaging system that also includes useful bands for vegetation and things like that. And so, and I think, let's see, these links, the links that are probably more useful are highlighted in blue here. Let's see. Okay, then there's also some places like this university in the Netherlands has gone through a lot of effort to organize data about different spacecraft and the different sensors. And one thing that's nice is that if you go find a particular sensor, like the multispectral imager from Sentinel-2, not only does it give you some details about the wavelength bands and the revisit time and things like that, and the resolution, but the also gives you links, in some cases, links to get access to the data. So they made put a lot of effort into that. Let me see if I can bring that up. Yeah, so here you can just see how the number of sensors in their database is just remarkable. And that one I was looking at was the multi-spectral imager for Sentinel-2, and that and so you can see that it goes through the bands and then gives you links to these not only the information about the technical information, but also how to get the data. So there's a lot of places to go fishing for this additional information. Let's see. Oh, and also this, I do like this article that's a summary of free imagery data sources. And not only does it include NASA and ESA ones, but also India and some others. Let's see. Okay, it is remarkably difficult to get a good comparison of remote sensing satellite data and the prices. And so I just put this up here as illustrations, but don't trust any of this data, because that chart on the left is really out of date. And then this other one that I found seems to be like a commercial service, and so I'm not sure if I trust their data either. But it's definitely something worth asking Airbus about. That just to clarify, if you were planning on building a commercial system or product or service based on using Airbus data in the future, what are the exact prices, retail and wholesale in some sense. But it just seems really striking to me that for years I've been curious about this, but hardly ever see any kind of good illustration of the data, of comparison of the costs. Okay, I want to talk a little bit about some of the different sensors. Generally, they categorize in passive versus active. Active meaning that it's actually transmitting something in order to conduct the observation. And from my friend Scott Madre, this is like a big category of all these different types of remote sensing, passive and active systems. From and there's a lot of ones are the main uses of imaging cameras and things like that. But there are other rather interesting magnetic sensors and measuring gravity systems, and people have come up with very interesting information that you wouldn't expect, like the quantity of water in the aquifer in California is measured with the gravity sensing spacecraft. So let's see, and this illustration is talking just about for the satellite sensors, that there's not only is there there's principally people are using CCDs for detectors, and it's really evolved quite a bit from, like, in 1990s there was the Hubble telescope CCD was sort of pushing the technology. It was 16 megapixels and it cost probably $100 million to build, and nowadays, of course, often your camera and your phone will have 8, 12, or 16 megapixels. And so there's been a real transformation in the technology. It's the visible light is definitely easier than there are infrared detectors down at that level, but it's also infrared gets very difficult for some of the systems only work with cooled system. But partly this diagram illustrates that there is processing on board on the spacecraft, and then transmitted down, and then processing, post-processing on the ground. And there's a whole variety of ways that people have come up with to scan or collect image data from snapshots and filters for different bands, to scanning across different wavelengths, to detectors aligned in a push broom, or it's that you move along, or trying to do arrays of capturing multiple spectra at the simultaneously as you do a push broom. And so this is an illustration of the NASA, what they call the A train, which is sort of replaced the giant spacecraft in the past, which is every instrument getting its own dedicated spacecraft, but flying along in parallel in order to observe almost at the same time. This was a chart from the Airbus presentation earlier, which summarizes for the Spot and Pleiades spacecraft the resolution and the number of bands and the multispectral. And panchromatic is basically black and white that but typically higher resolution. So on this Pleiades spacecraft, this spacecraft is basically this this large telescope pointing at the Earth, and the entire spacecraft body is all designed to make sure it's pointing at the spot you want as it orbits the Earth. And because it's always crossing the Earth around 10:30 in the morning, it's the sun is always above it, so that's why the solar rays are pointed up like that. Some of the other kinds of active sensors, you have things like LiDAR, which is it's like radar but using a laser, and so the LiDAR is typically sending like 50,000 to 200,000 pulses a second, and LiDARs are designed for different applications. A lot of them are designed to look at the atmosphere and the gases and the winds they're in the atmosphere, and they often choose certain longer wavelengths in the infrared. A lot of times the near infrared is used for the mapping of the terrain, and then but they can also penetrate into the water using blue-green colors going into the water. It's interesting that the LiDAR can actually pick up, a response from the tops of trees and the ground, and so you can get some kind of measures of the vegetation levels just by the difference in the pulse arrival times. So there's some various links in here that might be useful, but there's most of the LiDARs are focused really specifically on things like atmosphere or ice measurements or things like that. And so it's and it is basically a tiny spot that is tracked across the ground, and so it takes a long time to build up a full model of the terrain. And so it gives you very good precision for altitudes in the terrain, but is not great for detecting what the current crop levels are, things like that. There's quite a few people using synthetic aperture radar, which is basically this flat plane at the bottom of the spacecraft is a phased array radar, and basically the radar is actively sending out a beam and getting the reflection back, and the Terasar X one that Airbus controls the data for, and this is the Canadian RadarSat-2 spacecraft, and there's a lot of different complicated transmission modes that for mapping different regions. You can really choose to map in all sorts of things along the ground track. And there are projects about using. There's also this one link to a land care research work using Terasar data, and this is an example of what the Lincoln the research farm, the Ashley Dean Research and Development Station, looks like, and this is what it looks like with the colorized Terasar radar map. They color code these based on the changes from the previous pass of the radar satellite, so that you can see which fields have had been either harvested or grazed on, and gives you some information there. This just came from a PR image from Airbus on March 1st, and unfortunately I don't have the information about what date specifically that data was collected on, but through the previous Airbus presentation, they did show you how to get access into and look at fields of interest for your areas of interest that can pick up Terasar data for that. But it's definitely powerful for something like New Zealand, because this penetrates clouds and can be done at night also. Let's see. Oh yeah, talking about in general about visible and infrared wavelength bands. Okay, this is just a general picture of where the sun's profile of the sun's energy and our visible light, our eye has evolved to be using the light from the sun here, blue to red. And this plot is for how much is transmitted through the atmosphere. And so, for example, over here, this is where the where the ultraviolet it drops off because we're protected by the ozone layer and things like that. And so then you go out from near infrared, shortwave infrared. Well, and these people label it mid infrared and things like that. And then here, the Earth at Earth temperature, it radiates in this area, and this and it's the same plot down here, and you can see that around this area down here, the CO2, that's the absorption of the CO2 in the atmosphere that's the cause of global warming right there. And so so these are the atmospheric, the high points in this grayscale is the atmospheric windows. And so there's microwave and radio waves way out here. There's a visible light and infrared bands here. So in between here, all you would see from space would be the atmosphere. You wouldn't be able to see the ground from these other sites. So if you look at, here's one of those handbooks about Sentinel, points to this. Actually, this was a USGS, US government comparison of Sentinel and Landsat wavelength bands. And so over here on the left are the visible lights, red, green, and blue. And then everything else is into various parts of the infrared. And so this is definitely helpful in terms of, but it shows basically just block diagrams, block of range of the band for the wavelengths. So then say, okay, how can I get a little more detail about these, for example, the Sentinel-2 bands? What's the real detail here for that band? And that's where you go into these research papers, and they will say, oh, that band is actually has this shape, okay? And this looks like a complicated mess, but it actually tells you exactly the response of this detector for these particular wavelengths. Then there's this other site, which let me see if I can jump to it. It's an interactive site on Landsat users. Yeah, so this is this allows you to compare the details of bands against spectra of things like different kinds of plant spectra. And so if you look at this area, you can say, okay, bands 2, 3, and 4 have this response to this kind of spectra, and can you at one point, if you compare this band resultant band 6 or 7, can you identify the different kinds of plants that you're looking at here? But it's just it's getting to the point of having useful information on that detail, but it's still not a great deal of complexity here. There's if you go back to this, these are the menu options. They only have a handful of vegetation options to look at, and otherwise it's minerals and some aspects about water. It might be useful to look at the water turbidity and things like that, but you can see you're just at the edge of trying to get the real data that you need, where you have this complicated spectral response function for the particular spacecraft and sensor that you're looking at, and then you have the details about the source spectra of the vegetation or whatever you're looking at. So then another place that you can look at is this this complicated source spectra library. For example, at USGS, it is massive. It has it's mainly mineral focused. It goes down. You can get different kinds of soil mixtures, organic compounds. There's artificial compounds like, concrete or asphalt, things like that. There's some vegetation down here. As to whether or not if it matches your interest, I don't know. But it's, so for example, here's, pick one vegetation of number 2237, and you look at the plot, and it will give you a spectral response across this data for this particular kind of vegetation. And you can also, if you actually download the zip file, you can get in ASCII the values, the data values for that. But this is sort of where you began to run into the limits of the information of you need the if you were trying to figure out what you were seeing with the Sentinel-2 instrument with across their different wavelength bands on the details of these different kinds of vegetation or other materials that you detect it using this, and then you run into the limit of the resolution of the Sentinel-2 spacecraft. But I just wanted to give you some clues there as to where people are working on this and trying to build up these highly detailed spectral libraries of all these source spectra, and also and New Zealand is working on this as well. They have been working for quite a while on the spectral library for soils, and so this is there's maybe some context there for looking at the source spectra. Now let me just talk a little bit about some of the future systems. One over on the left here is just a general thing about the global space economy being about $360 billion a year right now. And it's interesting that the satellite manufacturing and launches are such a tiny part of this. Actually, the satellite services and ground equipment and things like that, and the applications are the majority of the satellite industry. And so, and it's really dominated by telecommunications, and agriculture and all these areas are growing quite a bit. And so that's, I really think that there's tremendous potential there for the kinds of things that you folks are working on as far as connecting these applications of data with with things that actually benefit the end users. This is just a snapshot of this Radiant Earth Foundation efforts to categorize and to different companies that are working in different resolutions of from medium to very high resolution, and then some of the startup companies that are coming on to develop systems for these areas. But once again, these are the data providers. They still need a lot of work from the data applications. And this is a general picture of just showing that in recent years, there's been a large numbers of commercial space activity. And here you see logos about data analytics along with the satellite companies and things like that. I give some of these links to some of the reports on some of the things like Bryce Space and Technology have good summary reports about these things. And there is a lot of effort both on the government, international governments, and also a commercial side for hyperspectral sensors. India and Italy have sensors, hyperspectral spacecraft that are up there. I don't know about the data access on those. I think they are still kept internally into those countries. There's also beginning to have some commercial synthetic aperture radar companies that are coming out. And so in some sense, as you develop, if you look at this in a longer term, systems that you design for addressing these areas will just have more kinds of data and more access to different systems in the coming years. And so I think it's a good time to be looking at developing systems that make use of this, irrespective of the challenge. And I think that is that's all I have for charts. Let's see. Oh yeah.
So I guess if people have any questions at all. Yeah, I don't see any at the moment.
So maybe, I hope some of the links in the presentation will be useful for you, and I'm certainly happy to follow up with any questions in the future about, as you're trying to track down specific information that you need. I just gave that, for example, that Sentinel-2 example, but the same kind of example for investigating the technology specifications for other spacecraft and sensors is the same kind of thing. It's a treasure hunt of trying to find the right information.
There we go. There's one question.
Oh. Yeah. Please follow up with questions later as you think about them.
Yeah, and you know how to reach us as well. Maybe along the same lines of that comment. Maybe I'll launch a poll here, just to see whether the session is something that is of use. All right. I mean, it looks good. So yeah, I think if there are no questions, we'll probably end early today. But just as a also reminders again, so we did record, and so you can actually watch it, and also. There is on the collaboration platform, I have actually put everything from all of the PowerPoint slides to the links to the video. They're all in one folder. And if you go to the platform, the latest discussion post there alludes to the actual link. So don't. So yeah, and I'll keep adding videos and the PPT slides on there as we go through the sessions. The other reminder as well is the check-ins. So thanks so much for those that have actually scheduled check-ins. There's quite a number tomorrow. We've done a few as well, and so I'm hoping to get all of the at least the needs and requests by sort of the early next week when we get everybody, so that we can do sort of group requests to potential resources and mentors as opposed to piecemeal. But if you haven't scheduled yet, please do so. It does help us to understand more and to potentially help you better. Let's see, anything else? No? All right. So next Friday, very similarly, UC, so University of Canterbury, is going to be the one giving a talk on UA technology, and then we'll go from there. So great. Yeah. Thanks so much, everybody.
All right. Thank you.